And I'll turn it over to you, Brendan. Thank you so much for joining us and taking the time to do the presentation. And thanks to everybody for joining us.
Great. Thanks so much, Gabby. And thanks to everyone to join and participate in the webinar and the conversation today. It's really appreciated. And just to, as Gabby was alluding to at the beginning, thanks for your patience with a couple of reschedulings. As Gabby noted, we had this, unfortunate large kind of cybercrime incident. And then previous to that, I'd been dealing with some folks getting quite ill. So it's fantastic to finally be able to be on the line and sharing with you today. So I'm Brendan McEwen. I'm Director of Electric Mobility and Low Carbon Strategies at AES Engineering. AES is an electrical engineering firm. We operate mainly in Western Canada, but we work on policy advising really across North America. Joined on the call today by Trevor Egan. Now, he may be listed in the participants as Brendan McEwen as well, because I forwarded him my invite. But Trevor performed a lot of the legwork on the design and costing work. So kudos to him, and he's on the line for this call as well. So as Gabby noted, Clean Air Partnership is working with a number of different local governments in the Greater Toronto, Hamilton area that are considering adopting EV-ready requirements. And so they commissioned us to do this EV charging infrastructure costing study with some generous support from the Atmospheric Fund. I'll note that for this project, we partnered with Mulvey Banani International Inc., MBII, who provided some guidance on sort of local design considerations and kind of the typical utility services and other types of issues that we would see for different sorts of building archetypes, and are providing peer review on the final report. So what I'd like to do in the presentation today is firstly, like the first half of the presentation would be important background information. So I'll do a very quick review of EV trends and context, and then speak to the importance of having access to home charging. I'll say a bit about what we mean by EV-ready parking, and also a quick introduction to EV energy management systems, which are an important technology to enabling high levels of EV-ready parking and of EV charging in notably multifamily buildings, but a range of other types of contexts as well. So, my, I guess, apologies for folks on the line for whom this is all a backgrounder, who may have even heard me do elements of this material before, but I think it's worthwhile just to ensure that we're all on reasonably the same page about what some of these terms are and the nature of these technologies. And then in the second half of the presentation, I'll review the costing study that we performed. So do a review of the building archetypes that we looked at and the range of different design scenarios that we considered for those building archetypes to be EV ready. And then of course, share the results. So in terms of trends and context, the most important trend to keep in mind when we think about the future of transportation is the decline in lithium-ion battery prices. So we've gone from costs of about, I think, $1,200 a kilowatt hour in 2010 down to, for 2020, the best data we have on industry-weighted average costs was $137 per kilowatt hour of battery pack capacity. So what's happening here is there's learning by doing, there's technological innovations and economies of scale. And for every doubling of manufacturing capacity of batteries, we're seeing declines of about 20% in the costs. And that's held true for about 30 years, basically, since lithium-ion batteries were invented. So what that means is it's fundamentally changing the economics of producing battery vehicles. So today, battery vehicles are more expensive to produce, and therefore, when they're not subsidized, they're more expensive to purchase. But within the next 5, 6, 7 years, what's happening is as those battery prices decline, we're seeing declines in what it'll cost to produce and then to purchase those vehicles. So these lines you see going downwards towards the right, these are battery electric vehicles with 400 kilometers of range in the purple, 300 kilometers range in the blue, and 250 of range in the green. We also have a plug-in hybrid with just 80 kilometers of range, as well as still a gasoline drivetrain. That's in this pink line up here, and conventional gas vehicles. And what we see is with the declines in lithium-ion battery prices, sometime in the next 5 or 6 years, the cost to produce and presumably purchase a battery electric vehicle without subsidies will be the same, and then subsequently lower costs than gasoline vehicles. So at that point, you're going to have vehicles that are the same and then lower cost to purchase. They're much lower cost to operate. They've got far lower electricity costs compared to gasoline, and also much lower maintenance costs. And they perform better in a number of respects, not least, of course, there's zero emissions. So it's difficult to think of why people are going to want to keep purchasing gasoline vehicles unless, of course, they don't have access to charging for those types of vehicles after that point. So this is technology and economics that are driving this shift. There are, of course, policy drivers as well. So just a couple of weeks ago, the federal government announced that it would be adopting requirements for all passenger vehicle sales to be zero emissions, which means they're going to be electric vehicles by 2035. It's interesting to note that both the Liberals and Conservatives have made these sorts of commitments in their platform. So if we see a fall election, I think we can still be pretty confident that something of this nature is going to be in place. And it's certainly not just Canada. There's a number of states in the US that are doing this. There's a lot of talk about similar sorts of US requirements that would be driving this as well. Just in the last couple of weeks, the EU has adopted this same requirement, and China is on a very similar trajectory as well. Other countries have made similar commitments. So all the auto markets in the world are moving in that direction, and that's driving a whole lot of investment in this area from vehicle manufacturers. And it's a really good thing for the climate. So this is the life cycle greenhouse gas intensity of different sorts of vehicle drivetrains, with different assumptions of how polluting the electrical grid is. So you see, compared to gasoline vehicles, battery electric vehicles in a jurisdiction like Ontario, which has basically zero carbon electricity, would be about maybe 15% of the emissions of gasoline vehicles. And all those emissions are just from the manufacture of batteries and of the vehicles. Now, as we get to greater renewable energy in the mining of materials, in the manufacture of vehicle components, those values can also go down considerably over time. So it's definitely very good news from a climate perspective. So with the improving economics of EVs, the most important thing to supporting access or supporting adoption of EVs is access to EV charging. This charging pyramid is a good way to think about where we need access to charging. So the base of the pyramid, the most important part, is home charging. Now at home, people will typically use either AC level 1 or level 2. So level 1 is like a 120 volt typical household outlet. Some households make do with that, but it does provide a very slow rate of charge. And most households want access to level 2 charging, which is 208 or 240 volt, somewhere between 16 amps and 80 amps. So that provides a faster rate of charge that is increasingly in demand for at-home charging. Probably about 75% of all the charging that takes place in Canada is at home. So it is critical to enabling EV adoption. If households are going to adopt EVs, they usually want to have access to that home charging. Now, there is also a fair bit of workplace charging that's provided. Probably about 15 to 20% of all charging in North America right now takes place at work. And then the remainder is either within metro areas and public locations, and that's usually through AC level 2 or DC fast charging. So kind of convenient top-up charging or opportunity charging. And then also when you're on long distance trips between metro areas, usually there's the need for very fast charging to enable those long trips. But again, the most important thing is access to home charging to enable households to adopt a vehicle if they're going to have a parking spot and a vehicle. A challenge is that whereas in single-family homes, it's usually relatively easy if you've got an on-site parking spot to add EV charging, not all the time, but usually easy. For multifamily buildings, it is, as a rule, costly and complicated to retrofit charging into those buildings. Usually this is done with the incremental addition of a couple of charging stations at a time, oftentimes maybe in visitor parking. And those incremental retrofits are expensive. So there's, of course, incentive programs at the federal level right now, as well as in BC. We've had an incentive program for about the last 5 years or so. But the average costs per charging station installed there over the last number of years have been about $7,000. It'll be more now with the increase in commodity costs for electrical infrastructure. So it's a real challenge, and it's not really a scalable solution to do these incremental retrofits. Now, it is possible, and we've been doing some of this work to do more comprehensive 100% EV-ready retrofits at a significantly lower cost per parking space, where you can make all parking spaces EV-ready in an existing building. So there certainly are advantages in the total life cycle cost of doing this. The challenge here is, of course, it's really difficult to get condominium associations and rental building owners to invest in these types of projects when they've got all sorts of other demands on their capital. And doing so, making the decisions around this is really complicated. And we run into issues, of course, where owners don't have the right sort of expertise to be able to manage this. And it is, again, a significant upfront cost. So it is typically best to future-proof buildings for EVs at the time of construction. So EV energy management systems are a really critical technology to enabling high levels of EV charging in applications like multifamily buildings. So what EV energy management systems are is basically charging stations that have some intelligence, and they can communicate across some kind of network like cellular or wireless or a cable in the wall. And basically, if only one vehicle is here plugged in charging, it could take the full capacity of this branch circuit. So in this case, the circuit is 40 amps, and it could take that full 40 amps and charge relatively quickly. But if multiple vehicles are plugged in and charging simultaneously, the charging stations communicate with one another, and they throttle down how much charging they're providing so that they don't exceed the capacity of that circuit and trip the breaker. So when you are sharing power in that way, you are charging at a slower rate for that period of time. But for a lot of applications, notably residential charging, that's just fine. A certain amount of sharing is okay. And when you're charging for an overnight period in your assigned parking space, everyone gets enough juice to charge their vehicles the next morning, the vast majority of the time. And what designing for EV energy management in these ways does is allow you to reduce the electrical capacity and therefore the associated electrical infrastructure costs that are necessary to provide EV charging. And therefore you can accommodate higher levels of EV charging, i.e. like up to 100% of your parking can ultimately have EV charging at them. So there's a range of different types of EV energy management systems and technologies and associated electrical configurations that they can enable. So these are some of these different electrical configurations. So a common and fairly simple form of energy management would be here in the top left, circuit sharing. So here across a branch circuit, in this case, we've got 4 charging stations sharing that branch circuit, and they adjust their consumption so they don't exceed the capacity of that branch circuit. Now you can also overload a panel and do the management at the panel level. And then there's technologies like feeder sharing, where basically we'd see this oftentimes in single family homes or in potentially townhomes, where from your meter, you monitor how much service is going into your electrical panel. And as long as there's sufficient capacity, you allow your charging station to charge the vehicles. if you're running out, if you're approaching the limit of that panel, then that charging station can throttle down or switch off depending on the nature of that control. There are also systems where this wouldn't happen on the feed to the panel, but actually on a branch circuit where you'd be monitoring the feed to the panel and then adjusting the EVC, which comes off of a branch circuit, or even sharing on a branch circuit between let's say, a dryer and an EV. So you can have one of those two loads on, but not both. And since we usually don't have our closed dryers running all night long, that provides perfectly adequate charging for the EV. So that's a range of technologies here demonstrating feeder sharing that can work in single family homes or townhouse applications, especially, or sometimes small apartments. And then lastly, we've got service monitoring. So with service monitoring, you monitor the amount of electricity that's being used by the building in real time, and then can throttle your charging stations up and down accordingly. So you don't exceed the capacity of the building or of a main feeder within the building. I will note it's sort of a useful design strategy for developers and electrical designers to be aware of, and also code officials. You can design for the ability for service monitoring to be able to be installed if necessary in new construction. So what you do is, if you would otherwise need to upgrade the service size to a building, and there's costs associated with that, of course, you can not do that and just ensure that you've got the electrical room configured so that you're able to install service monitoring if necessary. Now, the electrical code is inherently conservative. So what we see in multifamily buildings very consistently is that they are, transformers and service sizes are sized to a certain extent, but they may only use, after you get a couple of years worth of data, maybe maximum 30 or 40 or 50% of that capacity. So you've got all that additional sort of capacity to play with. So you can anticipate that that'll be the case. Design for yourself to be able to install service monitoring, but then a lot of times after you get some data from the building, not need it. This graphic just shows sort of the electrical demand profile of a building and how service monitoring can be of use. So this bottom line is the demand profile for a day in the building, and that's its peak at the highest point. And then if you don't have service monitoring, then the only power you have available to add additional EV charging is in the dash line area up to the capacity of the building. But if you do have service monitoring, then you can use all that time period, in the middle of the night, typically when vehicles are around, but other loads in the building aren't operating to as high of an extent. And you wouldn't need to, in this case, like upgrade the capacity of this new building to accommodate all those vehicles. So switching now to talking about what we mean by EV-ready parking and how local governments have defined this in EV-ready building requirements. So this is a building's electrical system with EV charging, and this is what we mean by EV-ready infrastructure. It is an outlet, so either a junction box or a receptacle, and then all the electrical infrastructure upstream of that in order to be able to provide power to that outlet. So usually this will be a junction box that then you could then in the future hardwire in charging stations. It is also possible to use an electrical receptacle that you can plug in a charging station in the future. So to be clear, I mean, this is probably pretty familiar for a lot of folks on the call who've developed in Toronto with the Toronto Green Standard, but it doesn't require that you'd have the charging station installed, just that you have the junction box there that's available to install infrastructure in the future. And again, either a junction box or a receptacle counts as an outlet. This is a list of jurisdictions that have adopted EV-ready requirements in Canadian cities. Most of these are in BC. To date, we've got, I think I'm missing one from the list here, but 17 communities that have adopted 100% EV-ready residential parking. This comprises the large majority of all the new development in the province. There's a couple of jurisdictions that have done just one EV-ready parking space per dwelling unit as the requirement that's on the books. Now, it is in Toronto's EV strategy to have 100% EV ready requirements in the future, and I understand they're engaging on that right now. Currently, the Toronto Green Standard requirements are 20% EV ready, with the remainder provided with conduit to facilitate wiring into the future. We are in discussions with a number of other cities across the country that have made commitments and various strategies to be implementing 100% EV ready, or at least exploring it. Likewise, there's a couple of cities in California that have adopted essentially these requirements, and a number of other jurisdictions we're working with stateside that are looking to do the same thing. So this is, a made in Canada best practice that I'd say is growing pretty rapidly. So when you're setting EV ready requirements, allowing for load sharing with EV energy management systems, it's important to establish EV charging performance requirements that dictate the maximum amount of sharing you can do, and basically how much power each vehicle needs to be allocated. So how much power EVs need to charge largely depends on how far they drive. So we were grateful to get data from the University of Toronto's Transportation for Tomorrow survey that they conduct for GTHA local governments. So they were very helpful in sharing these trip diaries, which record every trip that households take in their different vehicles. And so we had this great data set that had, for different parts of the region, how far vehicles are traveling each day. So this graphic here shows the vehicle kilometers traveled per day for different planning districts in the region. And you see for most of the areas where there's significant amounts of multifamily development, the VKT per day isn't going above, let's say, about 45 kilometers per day traveled. There are some areas where households travel a lot further. It isn't where we're seeing a lot of multifamily development, although there is a couple of exceptions. So at AES in the last couple of years, we've developed models that use the VKT inputs as well as other considerations, average vehicle mix and the efficiency of that vehicle fleet, average temperatures for a region, basically when it's, like I should say, the extreme cold temperatures. Basically when it's very cold, we would have higher electrical demands for vehicles because your heating will be on, and that takes power, as well as the batteries, at least the current generation of lithium-ion batteries, tend to require more power and may charge slower. And then also we make conservative assumptions around the arrival and departure time of vehicles. And there's some other considerations that go into this. And the model essentially solves for determining what's the maximum amount of load sharing we can do on a branch circuit, while ensuring that there's going to be enough electricity for the next day's driving more than 99% of the time, and vehicles will get a full charge to their battery more than 90% of the time. And it provides this sort of table. So it shows the maximum number of EVs that you can share on a circuit with a breaker of a given size. So on a 40 amp circuit, we're pretty confident that in many parts of the GTHA, you can get away with 4 share on that 40 amp circuit and still provide a really good quality of experience for your drivers. If you go to higher amperages, like let's say 80 amps, you can get away with proportionally more sharing. The loads are more diverse. So 10 share on that 80 amp circuit. So I will note that right now, the Toronto Green Standard version 3 allows essentially for 3 share on a 40 amp circuit. It says the minimum performance level is going to be 16 kilowatt hours average previous E over an 8-hour period, assuming that all parking spaces are used by a charging EV. So that equates to 3 share on 40 amp or 6 share on 80 amp. Based on the analysis we've done, we're pretty confident that higher levels of sharing are appropriate and will still provide a really good quality of experience for households that are living in parts of the GTHA where driving distance are relatively less. So let's say that average of 45 kilometers or less. As you increase the total driving distance, you can get away with proportionally less sharing. So much more exurban communities may want to consider having more stringent performance requirements. On the flip side, this is assuming that all the charging vehicles do is going to happen in residential buildings. We can be pretty confident there's going to be some workplace charging in the future that would actually be valuable for sort of wholesale power 20 years down the line, once all vehicles are EVs. And you'd want to take advantage of that cheap solar power that's going to make up a big part of the grid. So conversely, exurban communities might just say, well, we're going to plan for all households to be able to have access to some charging, but we're going to bet that those households will either be driving less on average and or are going to have access to other forms of charging as well. So I'll just quickly show a couple of diagrams from the analysis to get a sense of what we did here. This graph shows the charging power and energy in the battery for an example vehicle that was simulated over a couple of weeks. So here in the blue, we have how much energy is in the battery, and in the green, how much energy is being delivered through the EVSE to that vehicle. And so here in the first day, the vehicle drives a relatively short distance in that day and is sharing with a couple other vehicles during that charging period, but quickly gets back up to full charge. Then there's some days where they require greater charge, but even with some of that power sharing, they get the full charge. You can see in one of these instances, it goes a long distance, probably like 300 kilometers or so. And for that next day, doesn't get fully recharged, gets about 80% of the way there, but has enough capacity for its next day of driving and then gets back up to that full charge. So this diagram shows over the course of a year, the percent of vehicles that are not fully charged back up to the full battery capacity. So the overall vehicle days where you're not fully charged is about 5.5%. Now, and this is the percent of vehicles in a building that aren't fully charged. So there's a couple of days there where, maybe about a quarter of the vehicles in the building won't be fully charged, but the vast majority will have enough to get where they need to go the next day and then subsequently get fully charged. But hopefully that's most days it's a small percentage of the vehicles that aren't fully charged or none of them. And then the vehicles that can't complete the next day's driving throughout that year of simulations, it was less than 0.1% of vehicle days where you can't make that requirement. So there's just these few instances where vehicles can't complete the next full day of driving and would need to augment with, let's say, workplace charging or a public charging station. Oops. So again, the kind of key takeaway here is this table, which is what we would recommend as the performance requirements for most GTHA communities, where we say if we're using 40 amp branch circuits, we'll allow for 4 share on those branch circuits, higher amperages, relatively higher amounts of charging. So that was sort of the first component of original analysis we did, determining what are appropriate performance requirements. And then we also did this pretty comprehensive costing study. So in terms of the process that this study goes through, firstly, we do load calculations. So we have a series of building archetypes. And then for each of those archetypes, we figure out baseline load sizes in the building and the associated electrical systems in those buildings, if there's no EV charging infrastructure. And then for scenarios that have EV electrical infrastructure, update those load calculations. For all those buildings, we then do the electrical design. So we produce single line diagrams showing what kinds of electrical infrastructure is going to be there to provide that charging, as well as layout drawings that show the lengths of the branch circuit runs from panel boards to parking spaces to understand how much wiring needs to go into the buildings. And then based on those designs, we have an estimate of the incremental cost for all the different components of the electrical system to go from your baseline with no EV charging infrastructure to the building with EV infrastructure in it. And then, of course, present that in sort of interpretable graphics and information. So this is an example design for a mid-rise building archetype that we did that was using 4 share on 40 amp branch circuits with service monitoring. And so we've got the single line diagram here. We've indicated once you get your service from Electra, you've got a service monitoring EVMS equipment installed on the main service to the building. Then a transformer coming off of your main switchboard that's transforming from 600 volt down to 208 volt. And then that's being distributed out to various panel boards that are then serving 4 share circuits throughout the parking area. And we have the layout design for the wiring as part of that for this building. And then we do costing for upgrading each of the pieces of electrical equipment in the building. So adding that new transformer, what's the cost of that, all the different panel boards and the wiring and conduit to each of those areas. And then also communication systems. So in the baseline, we assume there's no communication systems in the parkade. Now, some developments might want to have, cellular service. We're using cellular for all these scenarios to, facilitate cell communications. But we're assuming it's not there. And so then there's an additional cost for cellular repeaters to be installed. And that gives us the total cost, incremental cost compared to doing nothing to do this development, as well as a cost per parking stall. That's the bottom line we see here. Now, we also looked at what would be the cost if we were to install this type of infrastructure sort of incrementally at a later date. And admittedly, this is necessarily pretty rough analysis. We basically applied multipliers that are reasonable estimates of how much it might cost to increment some of this infrastructure at a later date, and what that would mean for the cost per parking space to install that. I will say that if you do sort of a comprehensive 100% EV ready retrofit to an existing building, in our experience, it's going to cost less than this. It'll certainly cost more than a new construction and be a lot more complicated and difficult for a multifamily building to implement. But it is possible to do these types of retrofits. But I think these numbers are pretty representative. If you were to do this sort of piecemeal, a few kind of components at a time to make increasing amounts of parking spaces EV ready, which has been, I'd say, unfortunately, the practice for how buildings to date have been pursuing putting in infrastructure in these multifamily buildings. Pretty reasonable estimates of the cost of doing that, although there is a huge amount of uncertainty in this. So the buildings that we looked at 4 archetypes: high-rise, mid-rise, townhouse, and single-family development. So the high-rise was 16 stories with 405 units in it, 369 residential parking spaces, and then there was also 61 visitor spaces. It's not nearly as important to have any EV charging infrastructure and visitor. We don't recommend local governments make requirements for visitor parking necessarily at this point. So these visitor parking spaces weren't made EV ready, but the residential ones were. For mid-rise, it's a 7-story building, 150 units with 119 residential parking spaces. And then the townhouse development was a series of townhouse complexes where we would share an electrical service between multiple different townhomes in that complex. There was a total number of 19 townhomes, and each of them had a 2-car garage that was, private, associated with that unit. And then single family, 22 units in this single family subdivision, 44 parking spaces. Again, each of those households with a electrical service to that single family building, and then a 2-car garage there. So I'll walk through the different scenarios. Apologies, it's a bit of an eye chart in these complicated tables, but it's sort of the easiest way to represent the different electrical configurations that we looked at. So we have a series of scenarios here. They're numbered here on the left, and then this quick description of what they are looking at here in the second column, and the number of parking spaces that are made EV ready here in the third column. So the first two were meeting the current requirements of the Toronto Green Standard version 3. One with dedicated 40 amp circuits to each parking space for 20% of all those parking spaces, and one with the 3 share on 40 amp to 20%, which is allowed for in version 3. Then in this third scenario, we have dedicated 40 amp circuits to each parking space. So no load management is going on. You've just got a 208 volt 40 amp circuit to every parking space for 100% of parking spaces. We also looked at a 3 share on 40 amp scenario for 100%, 4 share on 40 amp, and then a 10 share on 80 amp. And lastly, 4 share on 40 amp with service monitoring. So these last three, C5 through C7, would be meeting the proposed performance requirements that our modeling adopted. C4 would be meeting those previous performance requirements that were in the Toronto Green Standard. And then basically all of these have the same circuit breaker amperage, except of course for this 80 amp one, which would have an 80 amp circuit breaker, and all the vehicles, or all the charging stations, I should say, would be capable of delivering 6.7 kilowatts. Now there's relatively few service providers, EV charging service providers out there right now who can implement charging on 80 amp circuits for these sort of low power EVSE, or sorry, not low power, but 6.7 kilowatt. Right now in the electrical code, it says you need to have EVSE that are the same power as the branch circuit. I think there's a good chance that'll be changed. It's not frankly, a sensible requirement to have. And there are also EV charging services out there that have an internal circuit breaker in the EVSE that allows you to do this. So we see this as becoming increasingly viable into the future. And I will note too, for all the high-rise scenarios, we considered the building located in both Toronto Hydro's territory as well as Electra's territory. So that reflects a good number of the sort of potential kind of primary distribution voltages that developments would be facing, and different utility policies developments would be facing in the GTHA. For mid-rise, we looked at the same scenarios. So 20% being EV ready for the first two, and then 100% for the last 5, looking at 3 share on 40 versus 4 share on 40, 10 share on 80, and then again, that service monitoring condition. And then for the townhome scenarios, we first had the 2 private parking spaces in a unit being served by 1 dedicated 40 amp circuit. So basically in this case, the household would install a charging station, and then they could just take that charge connector out and switch it between vehicles. Or there's definitely 2-headed charging stations if they wanted to do that, but that either way would provide them more than enough power. We also looked at a scenario where you'd have 2 share on 40, so that same connection from your panel for the unit to the parking garage area, but then have service monitoring. So the households would be required to install charging stations through some kind of covenant or strata rule or whatever it would be, sorry, condominium rule, to ensure they're installing charging stations that are going to be compatible with the service monitoring equipment for the building, and then you'd have service monitoring on the service that is feeding that particular townhouse complex. And we also looked at it with load switching. So in this case, you would be able to, you'd have control on a branch circuit, and you could charge your vehicle or have your dryer on, but not both. And what this was able to do was avoid upgrading a panel from 100 amps to the next largest size increment because of that additional 40 amps for charging. Here, we can accommodate it within the load calculation for that whole building. And then in the single family subdivision, again, just kind of the simple, have the outlet coming off the panel is a dedicated circuit, one outlet serving the two vehicles parked side by side, as well as with service monitoring for that building. So this was assuming something like RVs, DCC9 product that monitors that home's electrical consumption and then provides power to the EVSE if that's allowable. And that's, again, to avoid having to upgrade from a 100 amp panel to like a 225 amp. Now, I will note, like, as we move more towards electric buildings, I think it's pretty reasonable to expect that we'll have a much greater preponderance of higher amperage panels in these kind of Part 9 building formats. Electrification is going to take more power. There are, of course, all kinds of creative control strategies that can avoid that. But this is sort of the conservative estimate where we're starting with 100 amp panels and seeing if there's ways that we can avoid those upgrades and what that would cost. I think if you are in a building that has that 200 amp panel, it's going to be a lot lower cost, basically practically negligible in those cases to implement EV-ready infrastructure. So in terms of the results, this is the cost per EV-ready parking space in the building. So these first two ones are for the 20% EV-ready compliant with Toronto Green Standard version 3. And this is the estimated cost per EV-ready space for these different types of configurations relative to a building where there's no infrastructure in there. So of course, the total cost will be less. This is only for 1/5 of the parking spaces, but these graphs are per EV-ready space. And then here we've got the 500% EV-ready scenarios. So what we see is that, as one might expect, if you do this with dedicated circuits, 40 amp circuits to each parking space, you're looking at a relatively large amount of copper, significant utility service size upgrades to the buildings, and a much higher cost, in this case, about $5,000 per parking space. But C7 here, if you were to design for 4-share on 40 amp circuits with service monitoring, you can be 100% EV ready for the value we came to was, I believe, about $1,700. Actually, a little bit higher than a number of the other studies we've done in the past. A big issue is that, of course, construction costs have escalated so much recently, and these values are reflecting the costs in Q2 of 2021, according to RS mean. So it is reflecting, the significant increase in construction costs that we've seen. And then you can see that there's other ways of doing this, whether it's the 4-share and 40 amp EV ready or 10-share and 80 amp, that also are, at a lower cost point than, let's say, the 3-share on 40, or certainly than dedicated circuits to each of those parking spaces. For mid-rise buildings, broadly a similar story. One thing that was interesting here is that, at least for this archetype, we found that 10-share and 80 amp was resulting in the lowest costs, just a little bit over $1,500 per parking space for 100% EV ready. So it's worthwhile exploring a range of different types of design strategies for buildings to figure out what's going to be most cost effective, and then think about, well, what are going to be the implications for end users to use these types of buildings, and are we comfortable that there's going to be enough selection of EV charging service providers that are available for them. And then this is the results for the townhouse. So by implementing that kind of load switching with a load miser, where we're sharing a branch circuit between a dryer and the EV charging. We avoid a panel upgrade that you would need with service monitoring or just with that circuit into the parking space. And even with that, you know, relatively more expensive piece of control equipment, it reduces the whole cost significantly. So we get to $1,000 per parking space for that scenario. And likewise, using that kind of service monitoring technology, it's possible to get to, I think it was about $850 a parking space for that service monitoring scenario for the single family home subdivision. So putting that kind of service monitoring into each unit. In this case, when we have just sticking with 100 amp panels, it's kind of like a business as usual scenario for some developments in some subdivisions in Ontario is a useful sort of strategy. And lastly, you know, I'll just note that there's the costs of incremental retrofits that we would project would be significantly greater than making new buildings 100% EV ready. So that's reflected in this chart. Again, this analysis is kind of loosely indicative. There's a lot of variables that can impact the cost in retrofit sort of applications, but it does show the value in future-proofing buildings properly from the outset. So hope that's all useful and a good introduction to the study. We will be sharing the final report that will have a lot more detail in a couple of weeks' time, but really looking forward to the discussion now.